Hi, welcome to the fourth episode of the Javed podcast. Today, my guest is Ikram Gabiyev. He is a software engineer at Google. Hi, Ikram, welcome.
Thanks for having me.
Of course, of course. Ikram is a friend of mine from Amherst College. He was an upperclassman year above me, and he majored in physics and computer science, and did research in physics, and is currently working at Google. Before we start, I guess our conversation, delve deeper into it. Tell us a bit more about yourself, about your background, why you decided to major in physics and computer science.
Yeah. As a kid, when I was growing up, I feel like I was mostly interested in physics, robotics, anything that's got to do with tech, mostly. And I didn't know much about programming. I just was like, "Oh, this is fun stuff. I'd like to do this sometime again, maybe in the future." Um, I think it was about grade 5 or 6 when I started like learning more complex things about like robotics and electronics, and I got to a point where most of the articles that I was reading at the time were like, okay, like you're done building the hardware, it's time to program this. And I was like, damn it, like I want this thing to work, why do I have to program it? So that was my first introduction to sort of programming. I had this obstacle that I just had to overcome to make this thing work. um and at the time it kind of just seemed annoying, like as a kid, I guess. Later on, I think it was like grade 8 or something, a bunch of we have Ada University in Azerbaijan, which is a pretty popular institution currently. A couple of guys from there who were like sophomores just came by our high school and asked if there are any students around that would like to learn some programming. And I was like, sure. And it was completely free, so they were volunteering. So uh, that was great for me. I started like learning some C++ basics at the time, and I was like, oh yeah, this seems pretty fun too. So that's how I sort of just dipped my toes into physics and computer science, or I guess programming. Computer science is more of a vast subject. Programming is just one part of it, but that's how I dipped my toes into it. And later on, when I went to college, of course, I did some projects before that, but when I went to college, I was like, all right, I'm gonna try out both physics and computer science, and maybe I choose one that really interests me. And turned out that I couldn't really make a choice. I loved both, so I was like, guess I'm gonna double major.
And your experience at Amherst College, you're taking classes in research. I guess what were the most defining classes, and in your experience, which ones kind of solidified your decision that you want to pursue those majors and you want to stick to that path? Was
Yeah.
there like any life changing kind of epiphany moments?
Uh, I think in terms of physics, um, I, I think I took if we take into account all the life-changing courses that I took at Amherst, the ones that I took uh, from the list of physics courses, shall we say, were probably in the earlier semesters, and it was probably in my sophomore year or junior year that I took life-changing computer science courses. So physics courses had a larger impact on me, at least at first. Um, I took Intro to Mechanics. It was called like Newtonian Synthesis with Professor Hunter, who I ended up doing thesis with and like research with over summer. Um, and at the time, it was like, oh, wow, this is not high school physics. Like, there's a complete change of paradigm as you go from high school physics to college physics. In high school, I always thought, oh yeah, like I love physics, but it's like I don't love it as much as I do like engineering. even though physics is a huge part of engineering. But as I was taking the intro in computer science, mechanics, I was like, this is completely different. Now I have enough tools from like intro to calc, multivariable calculus at that time that I can, and enough understanding in general to go down to the basic first principles and use that first principles approach with like some basic assumptions to derive the whole mechanics by myself. That was essentially the point of that course, that by knowing a few simple assumptions and a few simple laws that can be relatively straightforwardly deduced, you can pretty much derive all the equations and mechanics. And at that time, it just seemed like completely groundbreaking. For me, it was just like, oh yeah, I've never thought about anything like this before. I just thought, oh yeah, just memorize this, memorize that, and then you're fine. But no, it taught me that if you go to first principles approach, you can pretty much understand, derive, or deduce anything within reasonable, of course, limits. And a follow up to that was the course in uh, Maxwellian synthesis, which is essentially, you know, electricity and magnetism, intro to E&M. Uh, that seemed very much fun. It kind of just followed upon the same principles. We used the same principles, but like in a different context. And labs were very much interesting, and the professor was amazing. Professor Hall, who was incredibly funny. His lectures are always entertaining to watch. Yeah, I guess at the time I thought, well, if I took two physics courses and if I'm this excited about it, I might as well just major in physics. Yeah, at that time I was absolutely certain that I'm gonna major in physics, and I guess computer science, whether I should major in comp sci became a debate. Yeah.
So, you bring up a couple of interesting points. One of the things I'm curious about is um, doing like why did you decide to do research in physics instead of CS, and then what made you kind of like switch from physics? Because it seems like your primary interest lied in the physics area, but then you kind of switched to computer science. Why did you make that transition? And how does research in physics feel in like, you know,
Hmm.
researching? Because I'm sure there are different fields of physics and there are different types of research you can do, but like, how can you know you will like research in physics, right? Like, how does it feel?
Yeah. Um, I guess a lot of things in life are about timing, and well, first things first. When I went to college, I was pretty much a kid. At the time, I was 16, turning 17. I
Mm.
think I turned 17 just before like the second semester freshman year. And I didn't know much about research at the time. I only had like, my own thoughts, maybe a few stereotypes. And one of the stereotypes I had at the time was that like, oh, there is no way comp sci research is as interesting as physics research. Like, what could comp sci research be about, right? And I took those two intro courses in physics. I did take like I skipped the first intro to CS. I just took the second one, but it was still intro. And then I took like the data structures thing. But those two courses were pretty much studying the fundamentals of things, right? I didn't have much time to understand what the research income side would feel like. So being excited more about physics at the time uh, just was like a more, I guess, it felt more natural for me to try and do research in physics as a freshman rather than computer science, just because I didn't have enough experience with taking computer science courses. So I studied, I looked at several theses of like students from earlier years with different professors, and I decided to apply. Uh, I guess you can choose like 3 professors that you would like to do research with, and number 1 was Professor Hunter. Professor Hunter, and he's doing research in cycling of thallium fluoride molecules. I can talk more about it later, but it seemed super interesting to me at the time. There's also a lot of quantum mechanics involved, and I didn't have much experience with quantum mechanics at the time, only high school stuff. So I thought, oh, this seems great. Let me try it out, and I really liked it. It was fun. There's a lot of if you're doing experimental physics, not theoretical physics, then um, things are completely different. In experimental physics, you've pretty much got the theory laid out already, which means you're mostly going to be working with data and setting up the experiments. And if the experiment's already set up, I mean, as a freshman, you're probably not going to do much setting up the whole experiment. You're just going to be like carrying out the various steps that were already established, and like collect the data and try and, I don't know, analyze it using various tools. So it seemed like okay. I had fun, but it was probably not like, oh, this is like fun. Like this is the most exciting thing that I've ever done. But I would mostly attribute it to the fact that I didn't have enough background knowledge as a freshman. Later on, I I kind of started taking more fundamental courses in CS, which I probably add the computer systems, which teach you computer system as a course teaches you how to make sure that operating systems, or how to integrate the hardware and like the software together using operating systems. Um, it's it was like completely life changing for me at the time too, because I was like, oh, there's a lot of, we're reading this textbook, um, and after each chapter you usually have like references to like various articles and papers or other textbooks, and I started paying attention to those like articles, papers specifically that were being referenced in uh, the lists, like at the end of chapters. And I started reading those papers, and I was like, oh, there's lots of research going on in like the field of computer systems about memory tracing, page swapping, various things that do seem to be have been there for ages, but there's still cutting edge research happening there. And afterwards, I took the class in networks, which seemed extremely relevant, with like the distributed systems and all. That seemed very interesting to me. I was like, oh, there might be a few research topics that would seem interesting to me in this area. And later, I took, of course, machine learning, and in machine learning, as you probably know, a lot of things are extremely cutting edge. Up to this date, people are coming up with papers, new models, and same goes with the distributed algorithms. Like I remember during the course, one of the lectures were studying what this kid in Zurich, in ETH Zurich, ended up inventing. He invented like a whole new model, and we were studying it. And this was done in 2019, and the guy was like 20 years old. So I'm like, there's quite some stuff that can be researched in computer science too. And this kind of just growed on me, and over time I guess I realized if I'm gonna do research, then it should probably be in computer science. But if I'm going to do research, quote unquote, in physics, then I'm probably going to do theoretical uh, physics.
Are
Yeah.
there any areas of, um, I guess, computer science or physics where you get to combine both computer science and physics? Like,
Yeah.
I don't know, I've heard about information theory, where you get to combine that. Are there like very active research areas where you get to combine, the quantum physics and quantum computing, physics and computer science essentially together?
Yeah. So information theory, I actually had a lot of fun studying it. I remember being really into it like later my sophomore year and earlier my junior year, because it's got a lot to do with like cryptography. Information theory introduces you nicely to like the land of cryptography. Um, there's probably not a lot of physics there. I mean, there's physics in everything pretty much in like computer science. I mean, all the signals and like, the hardware that software is using is built on top of physics. Uh, but I'd say that the most up and coming hybrid, like where both physics and computer science are heavily used, is probably quantum computing. Because traditionally, the way we're thinking about computing is with ones and zeros. You've got uh, you've got a memory that like you probably, and our viewers probably know about this too, but like your computer has different types of memory. You've got RAM, which is a volatile memory, which means it's all your memory is going to be erased once you take the power off or the battery off. And you've got your back in the day hard drives, or nowadays it's more solid state disks, SSDs, um, which by the way also use solid state physics to keep memory. I mean, all of that stuff is pretty much physics. First things first, solid state uh, physics is being used to keep to essentially replace the hard drives these days, and hard drives themselves used magnetic dipoles to keep track of whether one specific cell of memory has one or zero. But now with quantum computing, it's gone a level above that. Now you can use quantum states of um, anything pretty much. It can be a molecule, it can be an atom, doesn't matter. If it's got a certain quantum states, quantum state A, quantum state B, quantum state C, and quantum state D, you can use those to carry out computations and store information. And it can be done in parallel manners, and like you can achieve things that were not uh, meant to be done in like a single lifetime of a human being before. Like in order to crack passwords, you need years and years and years with like the current encryption mechanisms, these asymmetric encryption mechanisms. But with quantum computing, that can be decrypted in a second. So that's why currently researchers are trying to come up with ways of secure encryption and decryption to not like quantum computers decrypt all of our information once we get them to
So
work.
I've been hearing a lot about quantum computing on the news occasionally, right? Like, something Google does, something like startups in the field, but the it's still not really a mainstream thing. It's still very much in the development phase, right? What are the main challenges for the development of quantum computing, and what kind of physical, I guess, new inventions or discoveries can help to accelerate the process, right? To make it easier, to make it more, I guess, mainstream use of quantum computing.
Hmm. Um, Quantum computing is probably decades before it's going to be mainstream, if ever. Currently, it's only being researched in research facilities and certain companies, IBM, Google itself has a lot of quantum computing researchers, and um, there's if you've ever seen pictures of the device, it's mind-boggling. You've got like uh, huge, immense cryomech devices that help cool things down to like almost 0 kelvins. And at the very end, the bottom of it, the very most like bottom layer, you've got this one little chip that is your quantum computer. It's insane. Like insane amounts of energy are being used just to maintain that little piece of computer. And I guess one of the things that are the challenges about like the quantum computing is that sure we and this is probably going to require some at least basic understanding of quantum mechanics. Um, but in a nutshell, if you've got a quantum particle, once you measure its state, it's only going to have one state. Before you measure it, it's going to have a superposition of all the possible states that it might have. So, and this is a very simplistic view of it, just for the sake of the argument. But the problem is if you try and measure what the result is of the whatever problem is that you were trying to solve, you immediately defeat the purpose of the calculation because you know the reason that it's the quantum computers are supposed to be fast is that you've got all these different superpositions at the same time. Or I guess one superposition of all different states at the same time. Once you try and see what the actual thing is, it's already one state. So until you're interested in the actual result, quantum computers work great. But if result does interest you, it's not going to be much different, at least right now. So that's one of the dilemmas, I guess, one of the issues right now. And this is very simplistic to understand like actual quantum computers. One has to have a very solid understanding in quantum mechanics.
And why like newer superconductors like that can be super cool, right? Kind of like a big sink in the field. Is it because they can make the quantum computers faster?
Um, yeah, sort of. It depends. So superconductors in general are a thing because what causes resistance in materials, and this is probably people studying material physics know more about this, but when you have a simple wire, which is like, let's say, copper wire, with its atoms that, make up a I forgot the term, but like it's like it looks like a cage of atoms. There's a specific term for it. Oh yeah, lattice of
Mhm.
atoms and molecules. You have you have a bunch of electrons that are essentially conducting this current in that lattice, in those cages of atoms and molecules. And at normal temperatures, like any atom or molecule would, you've got vibration happening, right? The atoms are not standing in place trapped, they're moving around. And that causes that resistance um, for the current that's flowing through the wire. And if you cool things down just enough, ideal is like 0 kelvins, minus 273 Celsius. There's no vibration going on anymore. It's just a completely solid like completely stationary lattice of atoms, and you've got electrons flowing flawlessly. I don't exactly know in which respect or like why superconductors are exactly useful in quantum computing or what kind of benefits they give, but I imagine reducing the resistance to zero might might be a huge factor. Maybe it's being used to effectively trap particles, electrons in like one state. You can trap things, either magnetic traps and such. Uh, or I'm not exactly sure. I don't think electrons can be trapped, but at least maybe if you're trapping the lattice, maybe it's the state of the lattice that you're interested in. There are multitude of ways that superconductors can be used. And I guess the fact that you've got the lattice in a stationary state might be a thing. Yeah, but I'm not super familiar with it.
No,
Quantum
I just
computing is like completely different. Yeah,
yeah, I'm
yeah.
just
Just
curious.
theorizing. Yeah,
Yeah, no, no,
yeah.
that's fair. I was just curious myself, and I wanted to kind of like get your opinion on that. We mentioned quantum computing, and I'm learning a lot myself, right? Like it's very informational for myself too. You mentioned Google, and I guess let's start talking more about Google. You work at Google. You've been working there for a year now, right?
Um, yeah. It's been just a bit over a year. I think a year and 4 months. Yeah,
Year.
we've got a tool that keeps
Yeah.
track of like the
Uh,
yeah.
no, that's fair. So how is working at Google, right? Like what kind of projects you work on, um, what your like typical week look like, and yeah, like just tell me more about your work at Google.
Yeah. So I guess a prelude to like a preface, however you might want to call it, to my work at Google was my emerging interest in like how computer systems work at and like lower level stuff in general. And by lower level, not sure if audience would be familiar with it, but like you've got multitudes of layers in computer science. In general, we talk about abstraction layers a lot in computer science, where, for example, the lowest layer would be your hardware and how you interact with literal drivers and how the drivers themselves are implemented, how you can communicate with like hard disks and stuff. And at the very high level, you've got uh, code that's using all of the stuff that's below it to code up simple applications. Like if you're a game developer, you're not going to think about, oh, like uh, how do I make sure this specific byte or like 3 bytes, if we're actually talking about RGB colors, make it to this one specific pixel on screen. That would be extremely like quixotic, impractical to implement. Trying to uh, make every single pixel work. That's already been implemented. You can already use that. That's why we call it like a higher level layer. So my interest was growing. By my junior year, I mostly have been working on like higher level stuff, or coding up websites, maybe just some applications like mobile apps, and slowly this interest was emerging in lower level stuff, operating systems, and I can a lot of it I can attribute to some of my friends who started doing research in lower level stuff, operating systems, uh, stuff that's related to like memory tracing, for example. And I looked at my friends. I was like, oh wow, that seems like some really interesting research that you're doing. Maybe I can try and learn some of that myself, like outside of classes. And by the end of my senior year, I was like, if I'm gonna work at a company, if I'm gonna be a software engineer, I better be working on lower level stuff because that's what interests me most. And it seemed like it's an area where if I do end up doing research at some point, which is still a possibility, I'm definitely gonna do it like on lower level stuff. Um, but you never know. Never say never. So um, when I started working at Google, they looked that I've had some experience in Android, like Android mobile apps, but I also had this interest in um, lower level stuff. And at Google, which is really nice, when you're done with your interviews and there's the team matching process, they ask you specifically. They don't just look at your resume and be like, oh, this is what it looks like it's best for you. Maybe your interests have changed a bit and you're a new grad, so you have more opportunities to explore. They're gonna ask you specifically what you want, what kind of options would you consider, and yeah, they looked at the stuff that I filled out in the form they sent me, and they're like, yeah, uh, we've got this interesting team out here in Android. It's called at the time, like there are multiple hierarchies of like teams. There's a larger team called System UI, which is responsible for anything that you see on your screen in Android that is not the app. So you open up, your phone, you see a key guard, like the locking thing. We call it key guard. You swipe up, you unlock, you see the launcher, all the various apps. You see the notification shade, all the gestures that you're doing. All that stuff is system UI, and it relies on what we call window manager shell and window manager to work. It's essentially a service and a higher level abstraction layer created above that service to make it easier for other Googlers to use and or developers to use, that is being used for multitasking features. How do you manage different windows on screen? How do you make sure that this wants to request access to the screen to be viewed and this other app do not conflict with each other? How do you make sure that their layers are being composited onto a single display at the same time? There are multiple synchronization issues that come into play. You'll learn lots of stuff about concurrent programming. There's a lot of concurrency going on. In fact, synchronization is probably one of the most important aspects in this kind of work, because there are a lot of race conditions that might happen when you're dealing with concurrent code in general. Yeah. So yeah, I ended up joining the Android windowing and multitasking team. And if I would pinpoint to a thing that some of the stuff that we're writing, probably most of it, are not seen to the external users because it's being used by other it's mostly going to be used by other developers as like API. But one thing in particular that I worked on a lot has been what we call picture-in-picture. It's a general concept. iOS also has it. If you open up YouTube or any other app with video playback and you swipe up, you can continue watching it while working on other stuff. You've probably used it yourself, and a lot of people have, which I know for sure because I know at least like 5 million people have used it in a single month. Not personally, but like from the data. And it's yeah, it's exciting. It's the code base is extreme. It can be extremely complicated to understand, but you you use your knowledge in like lower level stuff, window manager service, and we call window manager shell to essentially change how people interact with this picture-in-picture service. Yeah.
So essentially, your typical week is mostly like writing new code and trying to implement that in the system, and then I'm guessing you have a supervisor that kind of goes over it with you, right? That checks the code and stuff. Is that how it goes, or?
In general, if you want to, I guess this is one thing about Google that you should always remember that whatever code you write is going into a code base that's being used by millions, if not billions, of users. So Google is very meticulous with the code that you write and the code that you upload. Whatever code you write, at least in Android, should be approved at least by 2 other engineers. And certain files and like parts of the code base request you need to request access from owners of those files, the ones who actually introduce those either concepts or like parts of the code base themselves. So in and of itself, it's not as easy to upload code at Google as if we compare it to like startups, for example. In startups, or as I've heard as well, you've got a problem, you've got a bug, you gotta fix it real quick, and whatever you have, just do some simple testing and upload it. It's like this agile mentality that like you gotta move fast, you gotta break things. At Google, it's more like yeah, you gotta make sure it actually works before you break anything. So
And
um, yeah,
what programming languages do you use when you write your code?
yeah. I mostly use Java because so in Android, Android is a complicated system. It's got multiple layers that I mentioned earlier. You've got lower level stuff that is mostly written in C. Those include different drivers. Android is in and of itself, it's built upon Linux. Linux is like this, the lowest layer in Android. So Linux is very much written, pretty much written in C. And then you've got some C++ code for drivers and such. You've got what we call a Dalvik virtual machine that is responsible for running your applications efficiently. Uh, it's pretty much written in C, C++, and then you've got, or parts of it, you've got some libraries in C and C++, and finally you've got framework code where we mostly work. It's where window manager is hosted, notifications manager, all these different manager services are in framework. And a lot of that is written in Java. And I'm not sure if you're familiar, but in Java you can also uh, you can use native native methods, right? You can link Java code to C code or C++ code. You can write your actual code in C and make it so that you can use it in Java by what we call JNI, Java Native Interface. So a lot of code that I write is in Java, but in the last, I can't recall when it came out, but there's also this language called Kotlin. It's a modern language that supports what we call coroutines. It's a different way of writing concurrent programs. We use it quite a bit in testing. We use it quite a bit in what we call integration end-to-end tests or clicker tests. And some of the new code, new parts of the code base, we're trying to write it in Kotlin as much as possible. There's still certain problems with it, like developing in Kotlin can be a bit slower. But Java is what I use mostly outside of work. I'm also like working on other stuff, doing readings outside of work and like working on certain projects. I mostly use C. So I'm not a huge fan of Java. I'd probably prefer C any day of the week. But Java is what I use mostly. At the end of the day, language is just the programming language is a means to an end. Whatever you use is fine as long as you implement the things.
What has been your like biggest learning curve in past year? Coming to Google, what was the
Mm-hmm. I'd say that there have been several learning curves. So in general, system UI in Android has a very steep learning curve because if you're a new grad, you probably haven't had much experience with Android operating system. You might have had experience with operating systems in general if you've done research on operating systems, but Android is a completely different beast. It's just its own system, and it's kind of niche too if you think. In Android system UI, you get a lot of bugs about, oh, like there's like this flicker that happened. Like I was opening up YouTube, I swiped up and I saw Google Maps for a second. And like those sort of bugs are very hard to fix because they're mostly have to do with race conditions. A race condition is when you have, let's say, one code base there's one part of code and there's a second part of code, and they try and manipulate something at the same time, use the same resource that is meant to be used only by one thread of of the application. So those things are very hard to debug, especially in a code base as large as the Android framework layer. So for the first 6 months, I was probably having a harder time trying to do debugging. Like the bug comes in, trying to fix it. I would probably fix like a bug in like 2 weeks. It would take me a while. And even if I had a fix, since this was especially true for the first 3 months, I remember just like uploading code, and I would get many, many, many comments about like the styling, the actual way I'm writing my code, and eventually it ended up improving how I'm writing code. But those 3 months, I wouldn't say they were tough, but I could visibly just notice that yeah, this is I'm not there yet. I need to work a bit more, and maybe I'll get used to it. And at Google, you're very much considered a noogler, at least until you hit your first year mark. So there is very little pressure. Everybody knows that there's learning curves, especially in Android, because the code base is so huge and complicated, and uh, it's not like there are lots and lots of books about Android operating systems. And even if there are, in fact, there are quite a few books, they might be outdated because Android OS is changing constantly. Um, yeah. So I guess that's a problem if you're trying to learn this thing. You have to start learning how to learn by doing things instead of just reading about them. We have this mindset from college that, oh, there's a textbook for everything. Well, I like don't know how I don't know, like modern physics. I don't know how special relativity works, right? In modern physics. So let me just grab a textbook, and I'm gonna be proficient in it in like 3 months or like a semester. Yeah, there is no such thing
Mm-hmm.
once you at least work on Android. I'm not exactly sure about other industries, but you're gonna learn by doing a lot, and I did learn quite a bit by doing. So it feels a bit satisfying. Yeah,
Makes sense. And so I'm guessing from what you're saying that working at a large corporation is still very much intellectually stimulating. It doesn't have to be a startup, right? And speaking more of Google, I guess Google is known for its unique culture and unique benefits, right? What are your favorite aspects of Google culture, and how does Google support your professional development and continuous learning?
yeah. First things first. A lot of people are probably gonna say food because food is free. In fact, that's at Google. If you're doing interviews, at the end of the interview, you can ask a question, and the most popular question is, "Do you guys actually have free food?" And the interviewers have been annoyed by that question for quite a while now. But I wouldn't say my favorite perk is food. It's probably the main like thing in the culture that benefits my style of work is freedom to do your own thing at your own pace. Of course, there are deadlines. Not as much if you're a new grad, but in general, there are deadlines or at least timelines, estimated timelines. But you're free to do the work the way you desire to do it. Like I like taking my time with things. That's usually my style. I can't move on to the next thing until I completely understand this one thing. Um, let's see. Do I have an example? Yeah, sure. There was this thing where users, and I can talk about it because it's public now. There was this thing where picture-in-picture users, so you're watching YouTube, you swipe up, uh, wouldn't have proper sizings and like in the default mode. Once you swipe up, it was either too small or too big, and we figured out that those users were mostly large screen users. So I don't know if you know, but like this Google device came out called uh, I'm gonna call it foldables because I think that's the public name. Google Foldable Pixel. It's like this phone that you can unfold and use it like that. Yeah, and you can fold and use it as a normal phone. Especially in those devices, which have square like displays. Um, Things were a bit weird with the sizings. I remember using it once, and I was driving and using Google Maps, and I swipe up and I'm like, why is the size so small? Who wrote this code? And then I'm like, oh, that's my component. I should probably go, fix that thing. So there were a few approaches where we could have a quick fix for it and make it work. But I remember taking my time with it and thinking that maybe there's a generic solution that would fit all devices. And if ever device with a weird display comes out, I don't know, like a circular shaped display, who knows, or some other shape, that we don't have to rewrite this thing again for like the whole sizing logic. So I remember really taking my time with it. I came up with like this a real nice looking mathematical formula. That was It was a while since I had done calculus by that time, but finally found a use case for it at Google. So I ended up writing this sizing code for the whole picture-in-picture thing. And I took my time with it. The whole size spec probably took 2 months to implement, maybe even more. But at the end, you know that what you implemented is a nice generic solution uh, of good quality instead of quick fix. And Google is really nice about things like that. They're like, yeah, take your time, whatever you need. Uh, just let us know that you're like working on this, on that. That's the nicest thing. It's also your schedule. You can make your own schedule. Back before last year's, I don't know, this was around November or something. Uh, we could work remotely all day, every day. Now it's like 3 days a week: Tuesday, Wednesday, Thursday. Um, but I do go to office every day, but knowing that you have this flexibility is also nice. Knowing that it's not a solid 9 to 5. You can come in if you want to. You can come in at 8. If you want to, you can come in at 11. Doesn't matter as long as you're effective doing what you're doing. Free food is also nice because you don't have to think about food at work. Yeah, it's at this point it's like kind of like college. Um, in fact, when Larry Page and Sergey Brin started Google, that was their main idea. Like they came from Stanford, right? They were doing their PhDs at Stanford. They're like, yeah, we want to make it just like Stanford. You go, you do your homework, you did your homework. You can go and we have like a volleyball court right outside the office. You can go play volleyball, or like there's a huge soccer field. You can just go play soccer, come back, do some homework, go back, get some food, and then you know do your own thing. So that freedom is probably the best benefit.
And how does Google support your professional development, like continuous learning?
Yeah. First things first, you you're gonna be all the expenses for like basic courses and stuff will be covered if you're like on some platform that you're using for educational purposes, and it's somehow at least vaguely related to your area. Like if it's got anything to do with computer science and it's like not a huge expense, sure, you can expense it. When it comes to bigger things, let's say you want to pursue masters, right? Google is going to cover 2/3 of your yearly expenses, like tuition or anything else for that matter, to up to 10 grand. So up to 10 grand, you're covered. And you can go get your master's. if you'd like. A lot of people, and I've learned about this recently, what they're doing is, you probably know, like Stanford is like extremely, like super nearby. It's in Palo Alto, and currently I'm in Redwood City. I'm based here, but my office is in Mountain View. So it's all in one place. It's like 30 miles here and there. You've got everything. So if you want to go and take classes for masters, like masters courses, you can do it online, you can do it in person, but you can also do it part-time, which is super useful. You can be like, I want to do just one single course or two courses like this semester instead of doing four, and you're going to pay proportionally to that number, right? Which is going to help you get those 10 grand to cover for the whole thing for the whole year. So you can take your courses part-time at Stanford. It's going to take more time, 4 or 5 years maybe, but you're going to be working too. So that's great. And at the end of the day, you're going to get your master's. Me personally, I don't care as much about qualifications at this point. I've got my undergrad degree, Google. I would mostly do it because, let's say, there's some topic that specifically interests me, and I figured, yeah, sure, I can like study it on my own, get a list of textbooks, and try and do my own research. But if there's gonna be like a huge benefit from taking this course at Stanford, sure, I'm gonna go and do it. And Google has enough support for things like that. Yeah.
And I guess one more question about the team dynamic, and your work there. So, if you have to collaborate on a project, how does it work? Are teams usually based on site, or is it like in different locations? How do you collaborate on projects?
Yeah. Um, Unless it's too, so we've got the Android windowing and multitasking team, and most people working on it are based in the US. So like you've got international Googlers and you've got US Googlers, and in the US you of course have multiple offices. So there are multiple levels to working with someone remotely. If you're working with someone in the US, it's much easier in terms of time zones alone. It's we got people working on Window Manager who are based in Taiwan, for example. So it's like what 9 hours, 11 hours of time zone difference. So it gets complicated to like communicate with those Googlers, but we manage it to work somehow. But it's harder. If they're based in the US, we have well, first of all, we have great tools to communicate with other Googlers remotely, so that's great. We have a lot of Googlers working in Kirkland office in Seattle, for example, and in our team we have at least two. So we communicate with them constantly. In fact, we do business trips to Seattle. I had a business trip recently, so like October, Kirkland. So you always make sure that even though you're working remotely, you also get to see your other team members and have some time to like work in person together with them. And they sometimes trips here too, and they do the same thing. A lot of people who I'm constantly working with are in person, and that is great, I think, because I'm just the kind of person who prefers working in person. Um, yeah, if I have a question, I'm just gonna, my manager's right to my left. I just turn around and I'm like, all right, here's the question. Just that kind of person. It's easier for me to communicate in person. So, in terms of the tools that we use, a lot of people probably are familiar with it already. If they're taking computer science courses, they're like version control tools, they're code review tools, code review at Google. The tool is amazing. It's probably the best thing I've ever seen. Yeah, outside, mostly in the open source world, people use what we call GitHub. It's like a code review tool. Yeah, but Google's internal tool review is an amazing tool. It helps, even if, you know, doesn't matter where your Googler is located,
I
you're
see.
going to have an effective code review
So
system.
I guess I'm curious about this. It's just personally, you've been doing this software engineering stuff for over a year now, and you're I'm pretty sure you know the news and the developments in the field better than I do, right? So I guess from your perspective, what are some of the most exciting trends in software engineering happening right now? And how do you see the role of software engineer evolving as AI and machine learning advances?
Yeah, hmm, good question. So there's always research going on in the field of computer science. Uh, I guess AI certainly comes to mind. AI, machine learning, deep learning comes to mind. Um, there are also other research areas. Like I'm actually I've uh, I've been interested in like hybrid of like systems research and AI, machine learning, deep learning research. Recently, I've been looking into how this thing we call page swapping works. There are certain implementations currently in, the Linux, Mac OS, and Windows operating systems. But there have been a few research papers recently that show that it can be improved with deep learning methods, deep learning models. Of course, there are multiple factors that come into play: the simplicity of the algorithm, the time, complexity, the efficiency, all that stuff. Yeah, but it's exciting to like try and find like a how shall I put this? To find a hybrid, to like find ways of combining or using deep learning, new like up and coming things in deep learning in like the more established areas of computer science, such as computer systems. Um,
Do you think with things like ChatGPT writing codes now, do you think there's a possibility that at some point Java or software engineering might become obsolete?
no chance that I'm absolutely sure about. There's first of all, in its current form, definitely not. Like, I've been testing ChatGPT and like Google's own version, which is called Bard, um, and it's publicly available, so everybody can use it. There's certain, uh, and ChatGPT uses it stands for generative uh, pre trained transformer chatbot, and the way it works, it's just it generates a piece of code or like any text for that matter using probabilities essentially. It computes, okay, like based on all the uh pre like all the data that I had in pre-training stage, uh after these set of words, what's the most probable set of words that I would usually um, read about, right? Like uh, if you have text saying how are like two words, right? How are your chat, your model is gonna say, oh, the most probable word after it is you, you. That may be a question. So that's how it works. At the end of the day, it's learned on the stuff that humans have produced. Um, so if, I guess it's like thinking about pseudo. This is an interesting analogy. If you're familiar with pseudo random number generators, it's like a way of producing random numbers uh, in a programmatic way. and those numbers are going to seem random to you, but after some point they're going to start being repetitive, and you're going to be like, oh, this is not actually random. That's hence the pseudo random. And I feel like there's a similar thing here. You've got a model trained on some data, and that data is mostly human made and human tailored specifically for these models. There's a lot of data processing going on, uh, although not as much in these transformer models. They take more raw data. But at the end of the day, you probably need some human generated data. It's also not at a point where you can ask it to do niche things. For example, Android OS code is completely open source. It's called AOSP, Android Open Source Project. It's online. Of course, there's like a certain lag delay between like the code that we write and the stuff that we publish to make it open source. But if needed, any of such models would be able to use that open source code to propose new things, new changes, or fix bugs. And however, I tried using chatbots to like attempt to solve bugs or like propose changes or even explain how the actual code base works. It's just way too complicated because you only have one code base, and uh, it's like a single resource that you're trying to make predictions upon. Yeah, all the generated. The funny stuff is that all this stuff that they generate these models, it's including ChatGPT. It's usually very vague, but they're very confident about it. So you have to be careful. Like you have to spot when what they're telling you is complete bullshit,
Makes
essentially.
sense.
Yeah.
We are nearing towards the end of our episode. It's been a very informational conversation, at least for me. Hopefully, our viewers will enjoy that too. I guess one of the final questions I would ask you is that, knowing everything you know now, what would you advise to budding software engineers who want to get into the field and who want to work at, companies like Google? How they can make themselves competitive, what they should do, how they should start, what resources they should use. Anything you could say would be appreciated.
Yeah, this is probably gonna be cliche, but I'd suggest finding your first of all studying on fundamentals. That's probably one of the most important things I could suggest. Making sure that you know you got your background set up before you dive into any niche topics, because you have to be, well, first of all, flexible, and CS fundamentals are going to be necessary for whatever niche topic you're about to research or study. So that's number one thing, get your fundamentals straight. Number two is find your niche thing. If you're in college, maybe try and do research in a certain topic. It's amazing how much one can learn if they're pushed by, I know, some kind of experiment that they're trying to carry out. Like I have quite a few friends who uh, learned uh, like amazingly learned like insane insane amounts of information about like computer systems or algorithms and that sort of stuff just by uh, getting themselves to do some research with like a professor, right? If you're doing research, you're learning fast. If you're doing something that's gonna push you by default to like learn things, read things, including textbooks, it's a good thing to do. Yeah. And when it comes to if you're in college, probably your senior year, your junior year, you should. I started prepping for interviews like in June, from what I remember, early summer. It was a like I had a good amount of time to study. It was probably 4 or 5 months to like read some of the classics or prepping the coding interview. You've got the algorithms manual by Sienna. Those are the things that I would suggest if you're applying for like a new grad position, if you're applying for a bit of a higher level position, for a those people probably know this already, but you'd have to like study system design, things like that. So you've got fundamentals, three things: studying fundamentals, doing something niche to learn more and dive deeper into certain subjects, because people want to see it on your resume. People want to see that you've done things here and there, but you also have at least one thing in particular that you are really good at understanding. That comes from research. Mostly, you can do personal projects too. And the third thing is prepping for interviews and doing the actual thing that would get you the job.
Uh,
Yeah.
what are the best ways to network in software engineering space?
Networking as yeah, as a computer science major, the first thing that usually comes to my mind is computer networking. But networking, I'd say use your alumni network. Alumni network is extremely helpful. Try, uh, trying, friends help a lot. If you've got a friend working somewhere, getting an interview is like a completely different beast from trying to pass the interviews. I've always thought about it this way, and I can't recall who told me this in college, but just find a way to get an interview. Just find a way to get an interview, however you can, and once you get it, it's a completely different experience. It's like getting an interview is different from passing an interview.
Nice.
Yeah.
Makes sense. Ikram, it was a very informative conversation. Thank you so much for your time and for the wisdom. And yeah, any other last words you have?
Uh, let's see. Any particular TV show suggestions? Yeah,
um,
can't think
I'll,
of it.
nothing in my mind right now, but if I think of anything, I'll let you know. But other than that, thank you so much again, and hopefully I'll see you in person very soon.
Right, right.
Take care.
See ya. Take care.